Alright, so in this video, we are going to try and answer the question, what is calculus? In calculus, there are primarily three objects of study. In the order that you will see them in your courses, you are going to learn about limits, derivatives, and integrals. To get an idea on what these three things are about, we're going to take a look at the following problem. Suppose you want to calculate the area of this figure. Now, this is a rather complicated looking figure. We don't have a simple formula like base times height to calculate the area. So what we're going to do first is we're going to approximate the area. Here's how we'll do that. First, we divide the area into 4 pieces. Now, the number 4 is not too important. What is important is that we are dividing it into smaller pieces. We are going to approximate the area of each piece, and then we'll add everything up to get an approximation for the total area. For now, we are going to focus on just this first piece right here, okay? What we're going to do with this guy is we are going to approximate it as a trapezoid. We do this by replacing the top curvy edge with a straight line segment. We can then use this formula for computing the area of a trapezoid. At this point, I want to pause briefly to highlight something that we just did. When we approximated this top curvy edge with a straight line segment, this might not have seemed very special. However, the idea of approximating something nonlinear with something linear is actually quite profound, and it is the central notion behind derivatives. Okay, going back to our problem, here is the figure divided into the 4 pieces. And here we have approximated each piece with a trapezoid. Adding up the areas of these trapezoids gives us an approximation of the area of the original figure. Now note there is some error. The first trapezoid here does not fully capture all of the area of the first piece, whereas these two trapezoids capture too much area. Now notice that if we divide the area into more pieces, we get a better approximation. For instance, here is a picture where we've divided the area into 10 pieces. As you can see, there is much less error now. In fact, you can hardly see any error at all, though of course there is still some error. We can continue this process of dividing the area into smaller, more numerous pieces, approximating each piece as a trapezoid, and adding up the areas of the trapezoids, getting better and better approximations of the area of the original figure. Now, a key idea here is that the actual area will be whatever we obtain if we continue this process ad infinitum, to infinity. And this is where the notion of limits comes into play. So limits help us in finding what lies at the end of an infinite process. And finally, the entire process of taking a complicated problem, breaking it down into a bunch of tinier, simpler problems where we can easily approximate a solution, combining everything together and taking a limit. All of this is the essence of integration. So to summarize, roughly speaking, limits help us in finding what lies at the end of an infinite process. Derivatives are used to approximate something complicated, i.e. non-linear, with something simple, i.e. linear. And integrals, the way I ended up wording it, integrals are a tool for combining infinitely many tiny pieces into a larger coherent whole. Then going back to the titular question of what is calculus, well, here is my answer. It's maybe not the best answer, but whatever. I said that calculus is the art of taking a complicated problem and solving it with some sort of infinite approximation schema using limits, derivatives, and/or integrals. So to end this video, I want us to take a look at the following math meme. Probably some of you have seen it before. Start with a circle of diameter 1. Since the diameter is 1, its circumference is pi. Next, draw a square around it. Note that the perimeter of the square is equal to 4 because the diameter of the circle is 1. Next, we remove the corners of the square. Note that the resulting outer polygon still has a perimeter of 4. Since the lengths that we remove in each corner, like here and here, for instance, those lengths are regained in each corner, like here and here, for instance. Every time we do this process where we remove the corners of the outer polygon, the perimeter remains 4. If we repeat to infinity, the outer polygon sort of converges to the circle. Now the outer polygon always has a perimeter of 4, and it converges to the circle with a circumference of pi. Thus we conclude that pi is equal to 4. So this proof that pi equals 4 uses a similar idea of an infinite process of approximations that we used before, but it gives us the wrong conclusion. The point I want to make here is that some care must be taken when applying the tools of calculus to solve a problem. So in your studies of calculus, you will have to take a look at some of the messy details that were left out of this presentation. All right, so that concludes the video. Thanks for watching.